Howdy, folks. Thanks for checking in Mr. Ulrich's Land of Biology. I am Mr. Ulrich. In the last set of notes, we talked about atoms and how atoms interact with one another to form bonds and molecules. And we even talked a little bit about carbon and how important carbon molecules are to life. We need to talk a little bit more about water as well. Kind of important little molecule that it is. Now, I'm hoping that you are familiar with the chemical formula of water, H2O, and even its structure. What we need to kind of get into is how that structure of water gives it its particular properties and how those properties play into its ability to be the solvent for life. It is a polar compound, and its polarity, excuse me, allows it to form a special type of bond called a hydrogen bond. Now, this hydrogen bonding is going to affect its properties and give it some, like we said, some neat properties for life. Its ability to stick to itself and to stick to other polar compounds, and how this affects the specific heat of water, as well as its heat of vaporization, and also density, how water isn't as dense necessarily as you get colder as we might think. The two hydrogens and oxygen that are bonded together to make a water molecule do share electrons between them, and so it is a covalent bond, but the electrons are not shared equally. Oxygen is a bit of a hog, so it holds onto the electrons a little more than the hydrogens do. We say that oxygen has a higher electronegativity. So this gives water its polar nature. The fact that the oxygen gets more of the electrons gives it a little bit of a negative charge, and then the hydrogens now just don't have their electrons, so they're just basically protons hanging out there, which gives them a slightly positive charge. So we get these positive and negative, or north and south poles. This allows water to act as a universal solvent. You got to put that in quoting marks because it will only dissolve other polar compounds. But a lot of compounds in life are going to be polar. The polarity of water is going to play a big role in maintaining structures like cell membranes. More of that later on. If we're going to discuss water as a universal solvent, let's make some solutions. Let's dissolve some stuff. Here's some salt. We're going to dissolve that in the water. Because I'm adding a little bit of salt to a lot of bit of water, then the water is the solvent and the salt is the solute. The salt water itself in total becomes the solution. So if I take some solvent, a lot of solvent, little bit of solute, add those together and I get a solution. The polar nature of water gives it what we call a dipole moment, or a positive and negative side, a dipole nature. When we get two dipoles next to one another, the positive-ish side of one molecule can be attracted to the negative-ish side of another molecule and form an intermolecular force, a force between two different molecules. In the case of water, we call this hydrogen bonding because it's going to be between the negative-ish oxygen of one molecule and the positive-ish hydrogen of a different water molecule. These are relatively weak. They are the forces that are involved in making ice, ice, and water, and water vapor, water vapor. When we compare the amount of energy needed to actually break apart a water molecule, compare that to just hundreds of kilojoules per mole, compare that to the 6 kilojoules per mole that it takes to melt ice, or the 40 kilojoules per mole that it takes to boil water, to break apart that water molecule is a lot more. So these are relatively weak. These are, if you remember, they're not between water molecules, so we find these IMFs or hydrogen bonds between other molecules as well. These are still between oxygens and hydrogens, but these are in the base pairs of DNA that have to unzip. We don't want the sides to fall apart. But it's all of these hydrogen bonds that actually make the double helix relatively stable in nature, because we put so many of them together and there is actually strength in numbers. When the IMFs form an attraction between particles that are the same, like two different water molecules, we call this cohesion. When the attraction is taking place at the surface of the water, we can get like a plane of water molecules that are all bonded to one another, and it forms kind of like a skin on the surface. We call this skin surface tension. Surface tension is what allows us to, yeah, float paper clips on the surface of water, whoop-de-doo. But it also allows things like water striders to be able to float on the surface of the water using the little hairs on the ends of their feet. We can also see cohesion at work when we see water on your freshly waxed car, or in this case, in this picture, on the waxy cuticle of a leaf. Because wax is nonpolar in nature, it doesn't bond with very strongly with water. Water and wax don't mix very well, and so all there is cohesion, and so the water kind of sticks to itself and forms these little balls that you can see. Now, when the attraction is between two different molecules, we do call this adhesion, just like glue is an adhesive. You can see this when water kind of sticks to you a little bit. That's the water actually adhering to your skin through IMFs. We also see this in a meniscus. Remember, I always read it from the bottom of the meniscus. For some reason, my students always remember that. But it's the adhesion and cohesion of water that actually allows that bend to take place, and it's actually attracted to the sides of the graduated cylinder. If I take that graduated cylinder and I make it more and more and more and more narrow, get it smaller and smaller and smaller and smaller, eventually you're not going to see the meniscus. All you're going to see is where it's pulled up the sides. And actually, as it gets smaller, it's going to pull it further and further up the sides. We call this drawing of the water against gravity up the tiny tube. We call this capillary action. And plants take advantage of this to go against gravity and pull water out of the ground up into the leaves of the plant. Unfortunately, capillary action is only going to get you about 3 inches or so, which is why bryophytes like mosses, they only get about 3 inches or so. So redwoods and other bigger plants other than 3 inches are going to need something else. It's going to need some help, and that's going to come in the form of transpiration. Transpiration is a process we're going to talk about in much more detail later on when we get into osmosis and osmotic pressure. But transpiration is the evaporation of water from the upper leaves. So as the water evaporates, that allows the water behind it to actually evaporate, move into that space, which allows the water behind that to move into that space, and all the way up the tree it goes. Like I said, we're going to talk about transpiration later on with much more detail. Another physical property imparted by IMFs onto water is its relatively high specific heat. That is the amount of energy that it takes to change the temperature of a particular substance. Water takes quite a bit of energy to heat up or cool down, for that matter. And so it kind of acts as a mellowing agent to other temperature changes. We can see this in climates of shore regions compared to inland, that the oceans can act as kind of a heat sink or a heat source. The other way that we can think about this is when it's really, really, really hot out, do you walk on the hot sand or do you walk in the water? I tend to walk in the wet sand because it's not going to burn the bottoms of my feet. But of course, that same sand, when the sun goes down, now I'm not going to walk in the water. Now I'm going to walk on the beach because the water side is cold and the beach is nice and warm in the cool air. Related to water's high specific heat is its relatively high heat of vaporization. Heat of vaporization refers to the amount of energy that it takes to do the phase change from liquid to gas. In the case of water, it takes 40.7, something on that order, 40.7 kilojoules per mole to do that phase change. Sweating is an adaptation that takes advantage of this high heat of vaporization, kind of pours water over us so that as the water evaporates, it takes the energy from the heat of our body to do that phase change. And then, of course, if it's actually changing phase, if it's so hot out that the sweat doesn't evaporate, excuse me, so humid out that the sweat doesn't evaporate, then it's not going to do its job now, is it? Speaking of different phases of water, we need to talk a little bit about density of ice. Most of the time when we talk about cooling things down, we get the molecules kind of closer and closer together. They're bouncing off of one another a little bit less, and you get them together until they're kind of just vibrating in space and they achieve their kind of solid structure. Water is a little bit differently. Yeah, we're going to pack it together. They get slower and slower as they get colder and colder until they bond together in this crystal lattice structure. Because in this crystal lattice structure, we have these kind of spaces here. I got the space here and a space here and a space here. I got these spaces where we could fit more molecules. That makes the crystal lattice structure a little less dense than the close packed jumble that we have over here in the water that's just a little bit warmer than the crystal lattice. So that makes the ice less dense than the slightly warmer water that's just around it. When we look at this on a curve, you can see where water is most dense. It is at a temperature that is higher than water that is frozen. So it's a little bit less dense down here than it is up here, and that's what allows ice to float. Kind of important if you're a fish that lives in temperate waters, that freeze up in the wintertime. If water froze from the bottom up, the little fishies would have a little bit of a problem. Plus, we tend to freeze lakes solid. We should take a brief couple moments here to address pH and ionization. I know we've been talking about the stability of a water molecule, the strength of the covalent bond between the hydrogen and the oxygen within the molecule, but it doesn't mean that it can't be broken. As water molecules whiz around and clonk into one another, they do dissociate. That does cause a hydrogen ion to break off of the hydroxide ion because the oxygen is such an electron hog. It's an electronegative. It takes the hydrogen's electron with it. The hydrogen becomes just basically a proton, and the hydroxide ion, that OH, has an extra electron whizzing it around. Now, because they have equal amounts, any solution of pure water, doesn't matter how much dissociation is going on, it's going to have equal amounts of H and OH. This makes it neutral. The number that we use, it's a mathematical calculation. There's other videos that you can watch that will show you how to go through the calculation. It's not magic, and it's not arbitrary, but the number of 7 represents neutral, equal amounts of H's and OH's. Arrhenius acids are those that add excess amounts of H but not OH, and so we get this imbalance. The number pH goes down as the number of hydrogen ions goes up compared to hydroxide ions. The other way is alkaline or basic. This is when you get the number above 7. And in this case, the imbalance favors the OHs. So now we'll have fewer H's than we have OHs. Buffers are weak acids or bases that when you add stronger acids or bases to them, they kind of take up the slack. They kind of resist the change, sudden change in pH. These are really, really important in our bodies and in the bodies of living things in order to maintain homeostasis. Our blood pH is regulated in a really narrow window, and it uses the relationship between the weak acid, carbonic acid, and the water in your blood in order to maintain that slightly basic, slightly alkaline characteristic that our blood needs. Well, we'll leave it there. Thanks for checking in. Again, I am Mr. Ulrich, and if you have any questions, feel free to leave them in the comments section here. If you're watching this on YouTube, send me an email. By all means, you can go and check out the website, see if there's any other tasty bits on there that can help you out. Other than that, we'll see you in class.